So after we done the short circuit test and open circuit test, that's the two major methods we measure the motor parameters. And next thing to introduce to you about different type of motor connection. So we have the star connection and delta connection. So that means in the future, when you see any induction motor, bear in mind, have a quick look about what kind of connection they are, and then they usually display on their nameplate. But sometimes some motor, they only provide you with free winding. You can do your own connection, your own wiring. So that means for tomorrow, when you do the lab, actually the motor you can do will be also configurable. You can configure with either star connection or delta connection. So let's have a quick look about the delta connection. So you can see here we have three type of winding. We can just connect it in a triangle, so-called the delta connection. So obviously you can see that our phase voltage across the phase winding, this is each phase winding, because it connects in such a way, so that means the input three-phase line voltage. We call line voltage. Line voltage means externally how we connect them, that the phase voltage will equal to the line voltage. So, and then we can also, the current for each of the line, when you go, the current come into here is split into two portions. And then you can see that the current in here, two current add together become this line current. But however, these two current are displayed by 120 degrees. So that means if you study the three phase, you can see that the correlation between the phase current and line current are also have a root-free relationship. So that's to say, if you measure any motor, of course, you do not know the phase current, you can only measure the line current here. But how do we know the phase current? Because we need the phase current to estimate the motor parameter, to estimate the torque. So you need to use the root-free in here to get the phase current. Bear in mind, the line current and phase current are also displayed by 30 degrees anyway. So that's a basic information. And for the phase voltage, they all add together form a triangle. So summation of all the voltage equal to 0 anyway. So that's some basic information you know that. And the power, we have two types of power we need to be careful. One would be so-called apparent power. So that means voltage multiplied by current. Of course, we got a root-free relationship. If there's a line voltage, we root-free. If the phase voltage, just multiplied by 3. Because phase voltage means 3 individual phase, we just multiply by 3. I think you learned that some time ago, right? If not, then you just remember the equation. And maybe sometime later, I can show you some internet material or website. There's a three-phase formulation are quite common. You can get it anywhere, but it's not difficult anyway. Just something look like where the root-free come from, mainly come from the trigonometric function. So you get it by yourself. Apparent power in here will be just voltage times the current. However, we got active power. Active power also means the real power, the real work done. Like a motor, if you go for some mechanical work, that must be the real work done. We call it active power. And then we multiply by cosine phi. That's our phase sort of power factor. The power factor usually vary from 0 to 1, but most of our motor, we're talking about usually 0.7, 0.8, or 0.9. So that's a common power factor we have. So that is to say, we also mentioned about if a motor or system have a low power factor, you can see that if this one is getting lower, then that means for the same kind of, if this is the same unchanged, then obviously the voltage, we don't change our PG&E voltage. So that means the current will be going up. So that means we require more current in order to provide the same kind of power. So that's why we like a motor or any power system to have a really high power factor. So power factor usually between 0 to 1. So typical power factor for motor may be 0.9, 0.8, 0.7. So many motor we see nowadays will be 7.9, 0.5 will be quite typical one. So that is to say, if you can able to improve the power factor, you can able to decrease the current. Decrease the current, that means you can decrease the conduction losses. And also you can decrease the cable size. Cable size, copper, is quite expensive. So you better do something about that. And then, of course, we do have star connected motor. So in here, we connect in star connection. So that is to say, you can see that our line voltage here, are split into two of them. So of course, they also 120 degrees between them. So that means you can see the voltage also have root-free relationship. Now the root-free multiplied by root-free become the line voltage. The current, so this current are actually flow into each of the phase. So that's why the phase current and line current are the same. So that means if you see any motor, then you need to use this formulation to get their own phase voltage and also the phase current, because we need that parameter to measure the internal configuration to get all the per phase parameter. Because we can, for any motor, we may not know what's happening inside, but we can only measure the output, the outside voltage and current. So which is our line voltage and line current. From there, if we know what kind of configuration, then we can obtain its own phase value in here. So that's something I just remind you. And usually the motor, if they are symmetrically or three-phase balanced, then this formula will be more accurate. But sometimes they may not be too balanced, because sometimes the motor may be, the bearing is not really good, not perfectly aligned, then some torque may be aligned to certain angle. In this case, the three-phase may not too balanced. But however, that's a perfect condition. So using this, that should be good enough to do that. So again, the apparent power and also active power also have similar formulation. So finally, just to remind you, just a table to show you correlation in each of the case, like the star connection and delta connection, how the correlation between the line voltage and phase voltage. So you can get all that relationship. So that's a really straightforward table. After you've done it for a few times, you're able to memorize them. So now then, let's conduct one simple example, so that from there, if you're able to understand how to work with them. So for instance, we have a three-phase, four-post motor, 400 volt and 50 Hertz delta motor. So we're now conducting the no-load test and the block rotor test. So usually we connect these two tests to study, to measure the motor parameter. This is really important. I think most of the experimental work, if we deal with an induction motor, we need to understand how to do the measurement. So the block rotor test and the no-load test is the major and important test. You must understand how to do it. In the exam, this must be there, because that's so fundamental, so basic. So that means we now have a voltage 400 volt and 8 amp of line current and 1,200 watt of power. And the per phase resistance is 1.2 because delta. So from the delta connection, you know how to configure the phase voltage and phase current, because we need to convert them into phase voltage current, depending on what type of the motor. And then similarly, we have the block motor test. Then we have this kind of parameter. So we are now asked you to develop this equivalent circuitry, like the T model we have. So we need to calculate all these components. So let's see how to do it. So that's a really standard way to do it. So for the no-load test, that means the I2 here, right? I2 here is not connected to anything, similar to a transformer without any load. Why is that? Because the motor torque is actually proportional motor current anyway. So when we do not connect anything to the shaft, no, so that means there won't be any torque, or the torque will be negligible, really, really small. There may be some kind of the vintage loss, but we just ignore them for the moment. So in this case, we assume I2 will be 0. So that means the current loop in the input side will just looping in here. So that's to say we got input voltage here, because it's delta motor, line voltage equal to phase voltage. And then we also have the delta motor, so that means we need to divide by √3 to get the phase current. Now we have the phase current, this phase current will inject to here, it is line voltage, 400 will go to here. From here, then we can quickly, then the power for each of phase divided by 3. Now we know the power for each phase. Straightforward, simple enough. Then firstly, we get the impedance. The no impedance is the impedance around this loop. So that means this loop will be 86. That's simple Ohm's law to do that. And then we have the resistive part. So that resistive part, we say we measure the real power during that time. So 400 volts divided by this current, then we give you this resistance. But this resistance apparently it may look like this resistance, but that may not be the case. Because when we measure the no load condition, the motor is rotating without any I2 current. So in theory, this resistive loss could equal the R1 resistance. But however, there may be some friction core loss we may not have calculated that. So this some resistance we just bear in mind will be something related to that. So we need to use other method to calculate R1. So that means, however, we can use the Pythagorean theorem to calculate the X part of the impedance. Yeah. So that means the X and L will be from these two components. Okay. So we get that. And then the rotational losses. You see we have the losses here. So we in the question we measure because the DC R1 resistance, we can just measure the ohmmeter to measure exactly the resistance, quite straightforward. We don't need to use any power testing. So usually we use ohmmeter, a multimeter to measure the winding, just put there to measure winding. So 1.2 ohm, so that's why we can actually measure the power loss due to the DC part of R1 resistance. So that means our power, this are the no power after we remove from the R1 losses. So that must be some kind of the rotational losses due to something. That losses could be in the open loop condition. There must be core loss plus some frictional loss or vintage loss. So that's how we can get. So that means this equivalent resistance could be due to two portions. One is due to R1, which you can measure directly using ohmmeter. The other part would be a kind of the equivalent resistance due to all the core loss and vintage. At the moment, we have difficulty to differentiate which one is which because it's a kind of losses we can represent by resistance. So that's how we get that kind of the resistance. But if in your motor, if the vintage loss is negligible, small, then you can assume this resistance equivalent to the core loss resistance. I think you do remember that when we working on T model, right? This one, we do have a resistance here. They got RC, right? So that could be this resistance. But however, this resistance could be also a component for vintage, friction, and also core loss. So this resistance will be a combination of a number of things. We don't know yet. So that's how we can estimate. All right. Any question up to this point? So another test we did is the block rotor test. The block rotor test, that means we are blocking the rotor, allow huge current to pass through from the stator to rotor. And because we're blocking the rotor, we are not trying to add really high voltage, otherwise blow up the motor. You can see the block rotor test, that means we hold the motor so that the rotor cannot be rotated. So you can see that we are not driving the rotor to allow the rotor to rotate. So that means the current must be quite large. So it's really similar to a short circuit test. So in this case, we use low voltage to drive the motor so that to avoid the motor being blown up. So we use low voltage, 100 volt, and then we can using the delta motor to configure the phase current, which will be 25 amp divided root 3, we got 14.43 amp. And the power we divide by 3, you just get the per phase. Usually all the equivalent circuitry, we have to use per phase calculation. So now then, let's calculate impedance. So now then we got the voltage here, 100 volt, and they divide by our current, that will total impedance for the whole block rotor test. So the block rotor test, we should have something resistant, and then we have some resistance here. So the whole path in here. Now then, you may ask me, oh, there's a impedance Lm here. Do we need to consider that? So usually when we have lower voltage, the Lm is related to the core loss. So that will be low voltage, low B field, the core loss will be small. So that's why we use low voltage for this kind of the block rotor test, so that we try to ignore this component. And then that means the whole loop here just more look like this loop of the connection. That's how we're trying to do. So that is to say, now that the impedance we are having will be the whole impedance here. The real part here, this resistance, more look like these two resistive components all together. And then from here, we use Pythagoras theorem. You can work out the X impedance part will be equal to 5 ohms. So that must be equal to, say, R1 here, X1, X2 dash R2 dash. So this must be something related to these two. So straightforward, very simple circuit law, no complication. So all these calculations are quite simple and straightforward, actually. But just new terminology to you all. So after this one, we use ohmmeter to measure the R1 resistance anyway. So that means total resistance, we just subtract it by 1.2, then we can get the R2 dash. Simple enough, without any complication. And for leakage, that means these two are so-called our leakage component. Then we now know the total. As I say, for motor design, we can only measure the total. You can see that the current path here are flowing in this way. No way we can know which one is which because they connect in series. So the only way we can do mainly depend on motor design. For good motor design, we use them to half-half. So that means 50% will go to X1, 50% go to X2 dash. But of course, for some other motor, they may use different design. So you need to go for what kind of motor they're using and see what kind of design they're using. Sometimes they use 4-6 ratio, maybe 3-7 ratio, depend on the particular motor design. But if the question is not given or the motor is not provided to you, then you can just using 50%. Because anyway, for most of the analysis, 50% will be good enough. Okay. Then for the magnetizing component, now then we try to get it. So for that low impedance, so 84.4. So just now we calculate that impedance, right? So that impedance could be due to the combination in here, right? So now then to get it, the exact value, then this 84, we can subtract this one from here, then we can therefore get the XL. Yeah, so that's one of the way we combine the two tests, we're able to get the magnetized inductance. So that's how we able to, so that you can see that this test, we can able to conduct most of the loss material. Then for per phase losses here, during the no, we have per phase losses, and then we minus the conduction losses here, then we can therefore estimate about the core loss. You see in the no test here, we are excited by the full voltage. For full voltage, rather than low voltage, because in block motor test, we have very low voltage. The voltage so small, the B field so small, the core loss may not be significant. We may not able to estimate properly about the core losses. But now then, using the low test, the full voltage here, then the core loss in here will be more significant. We are able to use this measurement to measure the core loss. So that's why in last part of here, we are using the per phase loss in the low, and then we minus the conduction loss due to the R1. Then remaining must be the core loss. So you can use this method to estimate the equivalent core loss resistance. That means will be this one, right? Lm, then Rc. So that's equivalent. Again, this core loss resistance is kind of the imaginary part. We cannot touch that Rc because it does not exist in the motor. We just imaginary to think that will be our equivalent resistance represent the core loss. This core loss, in a way, could be a number of losses, including the vintage loss, frictional losses, and the core loss together. So that's a kind of representation. So this is so you a very typical way how we can measure all the motor parameter. So from here, you see we have been using a number of estimation. We assume, for instance, this is 0.5x. Yeah, we're not quite sure depending on the motor. We also try to say in the block motor test, we need to use much lower voltage. So low voltage to make sure the motor will not blow up, will not be overheated. And then this low voltage, in this case, the XM, the magnetizing will be small, the core loss will be small. In this case, we can assume the whole current will be only looping in this R1, X1, X2, R2. So we can ignore the other component. So that's the key point we like to show you how we can using this so-called the open circuit test or the no test and also block volta test. The block volta test sometimes we also call the log volta test. Log volta test, some test book or some material, they all call it log volta test or block volta test. So remember, that's the two common tests you must know. When in the future, when you go out to any motor industry, you need to understand how to do that. So basic. Okay. Any question up to this point? The calculation is quite simple. Just simple Ohm's law, simple impedance calculation. No complication here. So I want to make sure you understand that. So I do another tutorial to you, just looking into the block rotor test. So this example is, again, have a three-phase motor. We have a 6-pole, 415 volt, 50 Hz, and star connection. Now this motor is star connected, not delta. So you can see how the correlation between them. And then you have following parameters. So you see in the block motor test, the full voltage 415 volt, but now we're only using much low voltage for safety. So you can see that it must be low voltage. And then current, we measure 35 amp, the power is 4.2 kW, and then the frequency we're using 50 Hertz. So sometimes some block motor tests, some engineers tend to use lower frequency too. The low frequency or the losses become even lower to be safer. But however, for convenience, we may not able to get other frequencies. You see our power point here is 50 or 60 Hertz. If you want to get something 25 Hertz, 10 Hertz is quite complicated, impossible, unless we have an inverter. So that's why some of the tests, we just use lower voltage, but it just retain the same frequency. So, and then we also conduct some measurement at 0.8 ohm per phase using ohmmeter to do the measurement. But this measurement, because we use ohmmeter measurement, the temperature we use usually only room temperature, say 25 degrees C. And then the operation temperature, why we have that? Because when under the short circuit test, the motor get very hot because we are locking the motor. So energize them with some voltage. The motor winding get very hot. So hot, the temperature usually go up. Say for this case, it go up to 75 degrees C. You see 75 degrees C approach the limitation for the motor. Anybody can tell me what's the limitation for motor temperature?
Maybe the insulation of the windings.
Exactly. The thing is, all the copper wire, if you go to any website, you search for the temperature withstanding for the copper wire enamel, the coating called enamel, they usually only can up to 120 degrees C. For really good, expensive copper winding, can go up to 180. So most of the motor you're using today probably only 120. So that means 75 is still under the limit, but if you keep energize the motor using high temperature approach 100, it goes to that limit. Then because of the winding, when you always operate at the upper limit, then the aging problem and also insulation may break down eventually. So you call it latent damage. So they may have more chance to break down. We don't like the motor breakdown. Most of motor breakdown usually will be the winding. Usually a motor can last for some 10 years, 20 years without too much problem. When we see the motor breakdown, we use always the winding. Adjacent winding there, then if the insulation are weakened, then when you have a transient voltage, you see our voltage usually here will be 120, really nice 120. But somehow due to transient, due to some large machine turn on, the voltage suddenly will jump. And then that transient will break down the winding, break down the motor. So that's why don't overload the temperature too much. 75 degrees quite a limit. But anyway, so we need to also understand the temperature coefficient to be this one. Now we are calculate the equivalent coefficient. So all the coefficient R1, X1, R2, X2 are mostly the series component, the least gauge component that can be calculated or measured by the block motor test. So bear in mind, because we are now using the operation 75 degrees C. So that means the R1 temperature, the one we calculate R1 resistance, that means this resistance only for 25, we need to calculate it at 75 degrees. Otherwise, the calculation is not sensible. So in here, we're just using the really basic formula for the temperature coefficient that which we learned in high school. We put in the temperature coefficient here and calculate the increase in the temperature and get back the actual resistance. Yeah. So because we cannot measure actual resistance, so in convenience, we can measure that should be good enough. So we need to do that. And then for the block voltage test, because star connection, so that means the voltage, the phase voltage, we need to divide by √3, so we can get this one, and the line current is unchanged. Then we can use this method, and then the power needs to divide by 3 for the per phase. Then we can get a per phase power. So now then, for the voltage impedance, then the voltage divided by the current, then we get the total impedance for the whole loop here. This whole loop here will be 1.979 ohm. So after we do that, we need to also calculate the power due to the real power 1.143. So these two using Pythagorean theorem, then we can use the x component. So the x component here, then that will be help us to calculate x1 and x2. But for the stator resistance, we have this one now. So that means this impedance consists of a few things, not only R1 resistance, but also the resistance due to the core loss or maybe vintage and frictional loss. So that means, and also could also have the rotor resistance too. So in here, this calculation would be, we have this resistance here. We know the R1 resistance. So in this calculation, we assume that we do not consider the other losses due to the vintage loss and also core losses. Because the block rotor test, we use low voltage. Again, the core loss will be negligible. Of course, the motor is not rotating. Not rotating, so that means we don't have any frictional loss and the vintage loss. So in this case, fair enough, we can use this method to calculate R2 resistance. So for the leakage component x1, x2, we have total here. Then we just divide by 2 to get the drop. So this, I don't know why I put the 5 here. Yes. Yeah, so that means that's how we get x1 and x2 anyway. But you see in some design, for some other design, I'm not quite sure I have here. For some design, we do another motor. They're using 4-6 relationship for some special lemma design. If you go to any website for lemma standard for motor design, we got standard design B, C, D, and a number design. They are rated that this ratio actually vary from 0.2 to 0.7. So that's why for the example, initially I want to say, it can be go up to 4 to 6 ways. So, but for simple analysis, we can just using 0.5 to show you some typical parameter. So in the future, if you want to measure the motor, you can check what kind of design method they're using. Some standard motor for the lemma design in the US, they do tell you it's a lemma design B, C, D, or H, or K. So from data book, you know what kind of ratio they are. You can see that for the block motor set, we can never measure the exactly individual inductance. We can only measure the total. So that's only an estimation. All right? Any question? So next thing I like to go further will be understand more about the torque equation. You see, we have been working on the torque equation for quite some time. Now then we further on understand more about the torque equation. Later on, we can start to understand the exact formulation for the torque equation. So we have the basic information for the air gap power. We have been talking about for air gap go through the rotor, we divide the two portions. One portion will be rotor resistance with the portion of S. Another portion will be the mechanical power with the portion 1 minus S. So that's what we know from the previous. So the heat air gap, we go to the rotor losses. So that is S ratio, the other one minus S is the mechanical output. So we learn about this. Let's go through the formulation to see what else we can get from there. So firstly, we have our conventional equation from previous chapter 9.5, then the mechanical power equal I squared R, so that is how we get them. Then typical mechanical equation, mechanical power must be equal to torque multiplied by the speed, right? And then for the mechanical in the unit of radian per second, then we can using the RPM, we can also relate to that. And then we also know that for the slip frequency, the rotational slip we relate to the synchronous speed would be 1 minus s ratio. We also know about that. But this rotational for the RPM, we can convert them into radian per second, become this formulation. Then we can also further convert the omega s between the RPM into this formulation. So that, and then we also have formulation for rotational speed, then equal to our basic, with this formula we always use for many times. And then hence we can convert this into the radian per second, because usually we use radian per second, then we can get this formula. So that's a few basic formula. We have been talking about quite a few times, the mechanical power only have the ratio of 1 minus S ratio to the mechanical output. So that is to say the mechanical power multiplied by omega S, not omega mechanical, right? Then this part also equal to the air gap power when we merge that information to that formulation. So that's to say air gap power actually using equal to mechanical power multiplied by omega S. So because we have the discount for 1 S. So very simple manipulation. Don't worry too much about it. It's very straightforward about the algebra. So that's to say what I want here to get you about the mechanical power actually equal to air gap divided by omega S, the synchronous speed. That's all for the thing. But having known about that, then the mechanical power are equal to this formula. And anyway, we get that. And then this is from the actual power. But when we refer everything to the primary side, to the status sign, then we put a dash in here to represent that. So now then I2 dash here from our T model, that is just a simple voltage Ohm's law. So that means our input voltage V1 divided by all the impedance, that will be I2 dash, right? Because you see that our model here, right? So we got the V1 here, then this all the impedance in here will be equal to here. So that's how we get the mechanical torque equation. So it's quite straightforward, only need 2 steps. Mainly, we establish this equation, and then we use the T model to work out the current, then that's why we get a relationship. The thing is, I2 current we need to measure, but voltage we can measure easily by using an oscilloscope or multimeter. We can therefore measure the input voltage. So that's why we like to represent the torque using the input voltage, and also all these are circuit parameters. So that means using circuit parameter and the input voltage, we can also know the slip. Slip is the difference between the synchronous and the rotational speed. We can actually get the torque. So that is a really important formula for induction motor. We are using basic parameter for the motor operation like the slip, and also like the voltage and the motor parameter, we can get the torque. So all the motor parameter, we can measure it by the log motor test and the open circuit test. So now then, if we like to plot the characteristic for this thing, then we can get this curve. So bear in mind, when we change the voltage, right? Change the voltage, then the torque will be changed. So like in this formula, I use the PU per unit value. That means if a full voltage, rated voltage 100%, then 80% of full voltage, I say 0.8 PU per unit. Per unit is something so-called the normalization, because I don't want to use particular voltage in here. I'm just refer to the full voltage. So called the per unit. So that means for when we change the voltage, then you can see that the peak value here, of course, will drop. How it drop will according to this formula or according to this formula. So you can actually using this equation to plot it to see how the torque will be changed. So you can see that there are more look like vertical, right? But actually, no battery. So here it look like more vertical, but actually slightly biased toward the right-hand side. And then these two are actually quite symmetrical. And then you can see that the torque actually proportional V square. So that means I can, using a simple representation to say the torque is proportional to the V square, just relate them by the weighted value. And then, of course, it's also proportional S. I can also relate it to weighted value for the S. So that means the torque, we can get the weighted value of torque like this one, weighted value of torque. And then when we get a new voltage or new slip, I can calculate roughly about the torque output from the motor. You see in this region, the S related to the torque are really much linear. So that's why based on this region to make up this portion to say the torque actually proportional to S related to the weighted S value. So that's how we can get this correlation. So this will give you a really simple method to estimate about the motor torque. Once you get the weighted torque for the motor, which is the maximum torque value here, then you can estimate the torque when you change the voltage or change the slip. But because all the motor we tend to operate in this region, that's a stable region, these curves are really much linear. So, however, for other conditions, when the slip is large, that means will be this region. Then the simplified formula could be slightly different. So you can see that when the slip is large, then in this case, slip is large, that means this no longer becomes small. When the slip is small, this becomes really large. But when the slip is equal to opposed to 1, then these impedance are much larger than R1 and R2. So in this case, we can approximate the torque equation by this formula. But we don't use them often because we're more focused on the stable region anyway. Then we're also interested in the starting torque. Starting torque is important because when we start a motor, the rotor is stationary. We want to see how much torque we can able to energize, can start the motor. Starting because a lot of static friction, which we need to make sure the motor start to rotate. So that's why when we starting the S equal to 1, so we can put all the 1 into the S in here, become this formula. So that means you can use the circuit parameter in order to get the starting torque. Anyway, these parameters are fixed, so you can see that the starting torque also proportional to input voltage square. So that's to say, this point are proportional input voltage square. So that's some characteristic I need to understand. So this kind of the motor torque characteristics are really famous, really popular. So you need to briefly understand how the important point look like, what's the peak torque look like, the starting torque look like. And basically in this point, that is the relationship to the torque. So the basic formula, you need to know that. So this fuse line is the most important part for the whole topic for induction motor. The previous chapter 1, 2, 3 is not important. So today's most important part I'm going to show you, but only 7 students here. So this is a shame. So remember, this is most important. The torque equation is most important part, and also the correlation of this is really important, and also the starting torque also important. You need to know all this basic information for induction motor. You give you some kind of the design method, how to design the starting torque for motor, and how to design about the safety region of this operation. All right, any question?
I have a question.
Yeah.
For the block rotor test, how do we know when to stop decreasing the voltage? Like, what is the point? Like, how do you determine that? Like, how do you determine?
That's a really good question. Yeah. And we usually try to use really low voltage, but there's no definition how much voltage we should use. So we usually use less than 20%. There's not any equation or formulation. It's just an empirical method. I myself have been used measurement induction motor. So I just scared to use high voltage and go up. So usually I just using 10%. If too low voltage, probably you can't measure too much about it. The power is too small. So usually 20% will be quite standard.
Okay.
You also need to be really careful because you touch the motor to see temperature will too high, not more than 80 degrees C, that we say. So you could do it carefully. Adjust the voltage slightly higher, the temperature won't be too high, then you have to do it over. So next, now getting more also really interesting about the motor control. How to control the motor speed. Of course, we have motor here, how to control the speed. So there's so many different kinds of the control method. The basic thing for motor, we must control the motor speed. It's the most fundamental method. Whatever you like how to drive the motor, but eventually you need to adjust the motor speed to your requirement. So even though you may say, I need to use the torque control, even though you control the torque, eventually you just control the motor speed anyway. So that means, let's see how we're able to control the motor speed. In the past, when we were working on DC motor, then we use line voltage, input voltage to do that. Let's see for induction motor, can we do the same? So let's see to do that. For instance, one of the popular application for motor driver is to connect the motor to a fan node, pump node. So all these fan node, pump node, rotational node, they are all related to the same kind of characteristic. The torque are usually proportional to the square of the speed. So like in here, I just try to apply the motor to this fan node to see what happens. So now then we use different voltage applied for the motor. You can see that if we want to adjust the motor speed, when we're using this full voltage, this is the point, the intercept is the point of operation. Then the speed will be in here. So when we lower the voltage, only about 70%, then I can lower the speed. When I'm using this one, I can lower the speed. So that to say, you can use different voltage. You can therefore adjust the speed. But obviously, you can see some a problem here. Do you think you can use the voltage to adjust the full range of the motor speed? Probably not, right? Because when you plot this curve for lower voltage, I think the low voltage will be probably something like that. Eventually, you will not see any intercept between the two curves. So that means this method is quite simple, but it's not good enough to have wide range of the voltage to speed variation. But it's just one of the good examples to show you one of the method, simple method, we can use the voltage to control the speed. Because usually when we do that, in the old day, when we don't have power electronic, we can only control voltage using probably auto transformer to control the voltage, but we cannot change the frequency. The frequency always at this point. So that means the crossover frequency usually about 60 hertz, we can't change anything. But we're able to adjust the voltage by using our auto transformer. So that means using this method, we can only adjust the motor speed in certain range, narrow range, only probably this range. We can't do much about it. But here you show you example how we're going to do that. So of course we can see here high voltage, we got higher torque value, and then all the curve here are passed through this zero crossing, the synchronous frequency. The synchronous frequency unchanged because we got the fixed synchronous frequency at 60 hertz. And then starting torque will have various kind of the value. But you can see that the starting torque also proportional to V squared. So when we have low voltage, the starting torque will be quite low. And then you can see that one particular thing, you can see that why we still use this method. Because for the fan node, the torque actually usually proportional to the speed square. So that means when the speed is equal to small, that means when the starting, the torque will be really small. So somehow we're able to start the motor. But however, for good range of the control operation, we may have difficulty always control it in a good manner. So that's how we can see the operation. So let's see an example how we can do that. So for instance, we got three-phase motor, 4-pole machine, 60 hertz, 480 volt, and then we try to do the following. So the rated torque will be this one, the rated speed will be this one. The starting torque, we at the 250 Newton millimeter. The breakdown torque, the maximum torque will be 450. So that is to say here, motor like that, you can see the breakdown, this is breakdown 450. The starting torque will be 250 in here. And then the motor is now driving a fan-load. So usually the fan-load proportional to the square of the speed. So like this. So we are now calculating the single speed and also starting torque at 0.5 pu and 75 pu, and also the motor torque at 1600 RPM, and also find the pu voltage at 160 RPM. So we need to adjust the motor voltage so that we're able to control at 1600 RPM. So that's one of the typical control method for induction motor. So this example is quite straightforward, actually. Firstly, we asked to calculate synchronous speed. So we have a really famous, we have been using this formula for many years, for many times. So that means it's 1800 RPM. And then we convert them into radian per second will be 188. And the slip here, so our synchronous is this one. The rated speed is 1740, so the operation speed will be 3.33. So that means you can see that there's a rated speed. So this one is calculate starting torque. Starting torque, we now have a good formula. We don't need to use full formula, but we know that they're proportional to V square. So that means our standard will be this one. So for other PU value, because we know that they're proportional to V square, so you can therefore get their starting torque. So using proportional manner. So that means you can see that if that starting torque will be good enough for those applications. And then for the motor, if you want to adjust the motor at 1600 RPM, let's see what happens. At 1600 RPM, then we can calculate the slip. So that's the calculation for slip. That will be 11.11%. Then we know that the relationship will have this relationship. So that is to say at 1 pu, then this ratio equal to 1. And then we now near the zero crossing, the slip will be proportional. So now then we using 1600 RPM, we now using 0.11, the rated slip will be 0.33. Then we use simple relationship, we can get the torque value at particular speed will be this one. When we know the voltage, we use the same formula, then we can calculate the torque will be equal to this one. At 0.5, we can also calculate torque to be equal to that one. So that's a quite simple relationship. You can see the formula look very complicated, but we don't need to use a full formula. We're just using the simple ratio in order to get most of the parameter. So now then, next step will be what kind of voltage will be needed to control at that particular speed. So we can actually calculate that. So the torque equation for the fan load, we are proportional to omega square. And then at 1600 RPM, then we use same formula. So that means rated torque 200, we got the rated slip related to the operation slip, and then we had the rated voltage. That's the voltage we need to calculate, right? So the output from the motor must be equal to the fan, right? When they operate together. So when we equate them, then we try to control the motor at 1600 RPM. So when we equate them, therefore we know this ratio. This ratio 0.8. So that means eventually the operation voltage will be 0.9 pu. So fair enough, quite straightforward. We can able to get all the parameters without too much difficulty. Any question up to this point? So you can see that motor control are quite simple. We're using some simple ratio. We're able to get most of the ratio, voltage, slip, and everything. So now then, try to finish off then, we see what we have done here, we deal a T model, which are quite important figures. So you need to understand the T model. And also for the block motor test, open circuit test, there's really standard method. You do need to remember how to do that. Go through my tutorial, then you can know how to do the measurement, which one you can approximate, which one you cannot approximate, which one you can measure the friction, windage loss, and also the core losses. So, and you can see that we are using per phase. Our problem for per phase will be we need to understand individual component per phase. For three phase, just now the torque equation, we did not multiply by 3 yet. That's important. They are all per phase torque. So for the full motor, you need to multiply by 3 because we have 3 phase. So do remember that. And then, but we are using per phase parameters. So we assume the three phases are balanced. If they're not balanced, the equation may not be too accurate. Then another characteristic, we know that the torque is proportional to slip only when the slip is small near the zero crossing. And the voltage is always proportional to V squared. So we can use the voltage to estimate about the torque using that voltage ratio to estimate the torque. And then in this chapter, we show you how we can estimate the control method by using voltage control. Voltage control is not a good control method. But however, we have been using this control method in the old day when we don't have the power electronic to control the frequency. Once the frequency, we can use inverter, we can control both voltage and frequency without any problem. So, any question? So, these are some block water tests you can go for, so you can understand more about what other people are using the block water test and log water test. Any question up to this point? We still have 10 minutes. We're not finished yet, so don't go away. So we just stop here so that stop recording. We go for next chapter.